Hello, everybody. Today, we're going to talk about something that trips up even experienced machine learning teams. Teams at Google, Apple, Meta, hospitals deploying medical AI. Say the team trains a great model. It has got high accuracy, beautiful metrics. The team validated the model thoroughly. It's the kind of model where everybody on the team is feeling pretty good about themselves. The team then deploys the model in the real world, and the model falls apart. That happens more often than we might imagine. In fact, it happens so often that there is a whole subfield of machine learning dedicated to studying this phenomena, to studying why this performance degradation would happen. And we're going to spend most of today's discussion on understanding the why as well. And more practically, we'll also try to understand what do we do about it when this performance degradation does happen. And here's the thread for today, summarized in one sentence, which is the test set that we build on our laptop or in our lab and the world out there, they are very rarely the same thing. And let me show you what that looks like at the scale of 1 billion devices. It's a story we all lived through, Apple's Face ID. When it first launched in 2017, it was trained on a huge collection of face data. By one report, there's more than 1 billion face images, infrared scans, and depth maps. It works in the dark, it works with hats, it works with glasses, thank you Apple. And Apple reported very low false accept rates. It was an incredible piece of engineering. Face ID checked all the boxes and Apple says, let's ship it. And for almost 3 years, it was great. Phones unlocked instantly, people stopped typing in passcodes, the technology just disappeared into our daily life. By any reasonable standard, Face ID was a deployment success story. It's the kind that we would put on the slide and teach our students about. Then 2020 happened, COVID happened, and suddenly everyone starts to wear masks all the time, everywhere. And we pick up our phone, the phone just stares back at us and says, well, face not recognized, enter your passcode. It happens again and again. Millions of frustrated users worldwide. And here's the strange part. Nothing was wrong with the phone, right? It's got the same Face ID, same chip, same algorithm. If anything, Apple probably have kept improving the engine across those years. A product that worked flawlessly for 3 years is suddenly failing everywhere, and not a single line of code underneath the product got any worse. So what actually broke? Well, nothing broke. That's exactly the point. The model stayed the same, and the world actually changed underneath it. Specifically, it's the input to the camera that has changed. The model was trained on full faces, and now it sees masked faces. The features the network used to rely on, say the nose, the mouth, the bottom half of our faces, those are simply not there anymore. They are simply not available to the model anymore. And the model is still trying to answer the same question, but it's like the question stem has changed. This is a perfectly good product met with a perfectly different reality. And this was such a big problem that Apple had to ship an iOS update with this line in the changelog literally being Face ID with a mask. And it's a $1 billion company doing an emergency fix because the data distribution changed. This phenomenon has a name. It's called domain shift, as our title suggests. We will also hear it called distribution shift or dataset shift. The data the model sees at deployment does not match the data it was trained on. And once we have the name for it, we will start seeing this phenomenon everywhere, in our phones, in medical devices, in self-driving cars, in pretty much every deployed ML system out there. But before we go spotting it everywhere, we have to learn to tell it apart from its look-alike. And the look-alike is one we have already studied, overfitting. Some of us might be thinking it already. Is this whole story just overfitting in disguise? This is a fair question, because both produce the same symptom, good training performance, bad testing performance. But symptoms looking the same does not mean the root cause is the same. And in machine learning, mistaking one diagnosis for another can lead a team to burn months chasing the wrong fix. So let us slow down and look at a concrete case. Here's a trained neural network on MNIST digits. On the training samples, it gets 97% accuracy. On the test samples, only 81%. And there is a big gap. It looks like textbook overfitting. And to understand if this is really overfitting, let's recall, what does it mean for a model to overfit? Recall that the quintessential signature of overfitting is a model that catered to the specifics of the training data, things like noise, pixel artifacts, patterns that only live in the training sample. And an overfit model is one that memorized noise and called it a feature. So is that what's happening here? To understand that, let's maybe poke around the activation maps. And activation maps are what each filter in a network responds to when it sees a certain input. It's the same spirit as a neuroscience experiment. Say you have study subjects and you see some study subjects would have electronic probe hooked on their head, and the scientist is showing the study subject a bunch of different stimuli and monitor their brainwave. It's the same idea here. We're just applying the same technique on a network. In particular, we fix the trained network, show the network different inputs, and record which filters respond most. Here we show the network the digit 4, and we see that in the first layer with 32 filters, the network is picking up basic strokes and edges, and we can still recognize the original digit. In the second layer with 64 filters, we see stroke fragments and spatial patterns. It's more abstract, but still clearly capturing structure. By the third layer with 128 filters, the representations are sparse and abstract. It's compressed codes that encode the identity of the digit. So the network is building a hierarchical map of features. And that more or less can give us the verdict. This network learned somewhat of a real visual representation. It doesn't learn pixel-level memorization. It's not weird noise pattern recognition. It's learning actual visual features a human would recognize as digit-like. And yet it still failed at test time. So perhaps this too much model capacity or overfitting is not the explanation. And we need to look elsewhere. And if we take a closer look at the test data, well, we quickly realize that the test data looks somewhat different from the training data. Right? It was rotated and shifted. The digits were slightly tilted, slightly displaced. And even though a 3 is still a 3 in the test data, it has been rotated 15 degrees. And we had quietly assumed the network could figure that rotation out on its own, perhaps because rotation just feels so effortless to us. But it feels effortless to us only because we, humans, have seen countless objects and their rotated counterparts. And this network has not. So our assumption broke. And honestly, we make that type of assumption that training data looks like test data almost every time we evaluate a model, often without realizing that we're making that assumption. But back to the network. The network never saw rotated digits during training, so the network naturally struggled. Not because the network is memorizing any noise, but because the input distribution shifted. And since there is no overfitting, the fixes for overfitting, tricks like regularization or dropout, they will not help here. In fact, throwing more regularization at this problem might even hurt because we would be telling the network to forget useful features it has already learned, meaning that the right diagnosis points us toward a completely different family of fixes. So we have two failure modes that look identical from the outside. And let me make this difference memorable with a story closer to our hearts. So imagine two students in this class. Both, unfortunately, did poorly on our exam. Student A, we interviewed them. They told us that they studied by drilling past exam questions. They never did homework carefully. They outsourced their homework to, say, ChatGPT. They never built the underlying understanding. Student B is a different story. They genuinely mastered a related course, the core course, the method course. But the semester got busy and they barely touched our CS Spoke course. They barely looked at our material. Hopefully we recognize that student A is overfitting. Their study strategy is catered to the quirks of the training sample. And the fix for student A is also clear. Actually engage with the material, build real understanding, stop pattern matching on past exam problems. Student B, on the other hand, is domain shift. We realize that no amount of studying the core course harder will automatically let them ace our CS Spoke exam because, while the deployment domain, the two classes, they are different. And the fix for student B is, importantly, not studying more the core course material. It's to actually look at some of the Spoke material. It's the same symptom between the two students, but it's completely different root cause, which leads to completely different fix. And before we help the student, we have to diagnose them correctly. And it's the same logic that can be applied to every model that we ship. So let's give the diagnosis a precise form mathematically. Domain shift mathematically means, well, there's this joint distribution P source of xy, which is not going to be equal to this joint distribution of P of xy under the target. And source and target here just means training and deployment. It's the jargon in domain shift context. In plain English, it just means the joint distribution we train on is not the joint distribution we're now operating in. And different joint distribution, this difference, it can break in three distinct ways. First, it's called covariate shift, which means, well, we'll see, the input changes, the rules would hold. The second type is called label shift, where the class mixture would change, where each class will still look the same. And a third kind would be called concept shift, which means the rules themselves change. The same input would be mapped to a completely different correct label. All these three ideas would look very abstract right now, but we're going to make them concrete through our discussion. And today we're going to focus on the first two, where we can not only diagnose, but also offer some clean fixes. We will close our discussion today with a teaser of the third kind of concept shift, the case that would break all of today's tools, and we'll pick up concept shift next time. So the structure of today is basically two diagnoses, two treatments, and then a teaser of a much harder third case to kick up for next time. And the reason we separate them is that each pattern preserves a different piece of the joint. And once we know which piece is preserved, the fix almost picks itself. So here's the first pattern, covariate shift. It can be summarized as the inputs change, but the rules do not. And let us make this concrete with a wildlife monitoring example. Say a conservation team builds a deer detector. It's trained on well-lit daytime photos in one forest. The model works great, the team is happy, the paper looks clean, then they deploy. And the deployment shifts along two axes at once. There is a temporal shift, nighttime instead of daytime, and a spatial shift, a different forest, maybe a nearby safari. On top of that, the night cameras are infrared cameras, not RGB cameras. And the team noticed the accuracy plummets. Something about this new forest, this new lighting, this camera, broke the model that looked almost soft a month ago. And here's the thing, a deer in a different place at a different time is still a deer. It has got the same deer ear, same deer legs, same deer antlers. The deer have not changed species, and the model has not gotten any dumber. What didn't change is the relationship between deer features and the label deer. If we showed each other, humans, a night vision image of deer and asked, well, is this a deer? We can still tell. And this is a key intuition, namely, if a human can transfer the concept across the visual change, the concept is preserved, only the pixels moved. What changed is the background, the lighting, the vegetation. The pixels look completely different, but the rules are the same. And if the rules are the same, then intuitively, all we need to do is help the model see the new pixels as just another flavor of deer, not a completely alien input. And this shift is called covariate shift. Covariate is just a fancy word coming from the statistics community for input variable. The covariates, the axis, the features, they shifted. In particular, P of X, the distribution over the inputs changed. The inputs look different. P of Y given X, which describes the rule, that stays the same. The rules are unchanged. Let's see the math underneath it. We can break or decompose this joint distribution, P of XY, into a product, into P of Y given X multiplied with P of X. And this decomposition is just the chain rule of probability. And it lets us isolate which P's moved, which P's stayed constant. In training, P of deer given an infrared image might be contrively 20%, and P of an infrared image might be 5%, and the joint might be 1% by multiplying the two. In deployment time, P of deer given infrared image is still 20%, but P of infrared is now 90%, so the joint jumps to 18%. So this contrived numbered example tells us, well, same conditionals, different input frequencies can indeed lead to a different joint, as the decomposition tells us. In plain English, the rules of, well, what counts as a deer given these features, this question, this rule, did not move, but the kind of images we see all the time, that did move. And that is how P source became unequal to P target, even when the underlying rules have not changed. And this exact pattern is worth almost real money in the real world. Let me show you how much. The highest stakes version of covariance shift I know of, being someone coming from the robotics community, is sim to real in robotics. Here we show a bunch of figures. The first figure is from Tadric's group, a Franca arm with sync cameras and a wrist camera. On the evaluation side, a nominal setup, then an object-centric shift where the objects are rearranged, then a station-level shift where the whole workstation layout changes. We notice that even small rearrangements create domain shift for the robot's vision system. The second figure is from Madukro, and the top row shows real robot workspaces, a panda arm in a kitchen, a humanoid at a tabletop. The middle and bottom rows show simulation counterparts of the same tasks. We can see the visual gap immediately. Lighting, textures, camera angles, object appearances, everything differs. The simulated mug just does not look like a real mug, even to our human eyes. And if we, humans, can tell the difference at a glance, a vision system, a vision-based policy trained only in simulation, certainly can pick up that visual difference. And transferring from simulation to real world without adaptation leads to large performance drop. That is sim to real gap. It's the same task, but very different sensory inputs. The grasping rules did not change, gravity did not change, the cup is still a cup, but every pixel reaching the policy through the camera looks very different from what it was trained on. Now, here is why this example matters beyond the diagnosis, why this example matters in real-time or money terms. Imagine a robotics team who trained a manipulation model in simulation, and the team wants to convince a client that their robot can work reliably in the client's factory. Today, what that means is physical experiments. And in the physical experiments, the robot might break, the team might need to hire a dedicated engineer just to babysit the robot, and every iteration costs days and dollars. If we could close the sim to real gap, then every one of those iterations could happen cheaply inside a physics engine instead. So this is not a story about prettier graphics. It's a story about whether robotics can iterate at the speed of software, or does it have to iterate at the speed of breaking hardware? Now let's bank the pattern, because covariance shift is everywhere in real systems. Recall that in Face ID, masked faces changed the input distribution. Our identity did not. In the MNIST rotation example, well, we have rotated pixels, but a 3 is still a 3. And for sim to real robotics, simulated versus real textures, but the grasping task is the same. The signature is always the same, and once we get a taste of it, we start spotting it in our own projects. Namely, if a model works on the lab data and fails the moment we ship it, covariance shift is one of the first things to suspect. But diagnosis is only half of the job. Once we have diagnosed covariance shift, what do we actually do about it? Recall that in every case of covariance shift, we have this requirement that P of X is allowed to change, but P of Y given X stayed the same. The rules stayed the same. And isolating which piece is stable, which piece is constant, that's exactly what tells us which fix is available. Because when the conditional is held stable, we can link on it. And this formal idea is called importance reweighting. Here's the intuition before we show the formula. Recall that in vanilla training, in vanilla empirical risk minimization, we would take a pure average over each individual data point's loss. By reweighing, resampling, or importance sampling, we would count contribution of certain data points more. What data points? What certain data points? Well, the ones that we expect to appear more often in the target domain. So formally, we would weigh each training example, training input, by this W of X, a ratio. This ratio is equal to P of X under the target domain divided by P of X under the source domain. So by this ratio, examples that look like target domain inputs, well, they get unchanged. Examples that only live in the source, they got heavily pushed down, they got downweighted. And let us walk through this figure together. The x-axis is a feature, the y-axis is the label. We have two types of color dots. The blue dots are the training data, the gold dots are the target data. The dashed line sinusoidal wave, sinusoidal curve, is the true conditional P of Y given X. And it stays the same for both the training and the deployment, for both the blue and the gold. This is exactly what the covariance shift assumption requires. If we treat every blue dot as equal and fit a linear hypothesis, for example, then we get a line with a negative slope. But look at where the gold dots live. The target data actually sits on the other side of the input range where we would have wanted a positive slope. So we apply this reweighting idea. And we realize that after reweighting, the blue dots get different sizes. The blue dots that look like target data, they get enlarged in the figure. And those are the training points we are double or triple counting because, well, these are the training data points that look more like the target data. So once we do this reweighting and again fit a linear hypothesis, we see that the fitted line now tilts positive, which generalizes much better where deployment actually lives. Notice that we're not changing labels or inventing new rules. We're matching training emphasis to deployment reality. And the trick, in essence, is just to pretend that the deployment distribution was the training distribution all alone. Kind of fake the training distribution to look more like the deployment. Reweighting is elegant, of course, but it's not always practical because we need it to evaluate the ratio between two distributions. And even if we cannot have the exact probability numbers, we still have to somehow estimate those probabilities. Otherwise, we wouldn't know how much to enlarge those blue dots. And estimating those probabilities themselves can be hard, especially if your data lives in a high-dimensional space. So if we do not know those P of target of X well, meaning that, well, we do not know where the gold points actually scatter along the feature axes, the ratio will just become unreliable, and unreliable weights can hurt more than they can help. In those situations, data augmentation is the practical workhorse. Actually, almost all systems out there use some form of it, often without even thinking of it as a domain shift fix. The idea is to create new training examples that mimic plausible target conditions so that we can expand the variety of inputs the model has seen. So rather than reweighing the data we have, we manufacture more of it in flavors that look like what we expect at deployment. The core rule is, well, an augmentation is valid only if it does not change the correct label. Typical augmentation tricks include a horizontal flip, for example, in Vision, a random crop, a color jittering. These do not change the label. But not every transformation is safe. If we're doing OCR, optical character recognition, we're trying to recognize letters, then we should not flip a letter because, for example, flipping a B, we might get a D. The labels would change. Similarly, digit recognition, we should not do rotation because rotating a 6 and we get a 9. And other examples include medical imaging. For example, if we crop an image, we might cut out a tumor. And now we have an example that is labeled tumor present while no tumor is in the image. The label's changed. So augmentation needs domain knowledge. A good augmentation pipeline is not a one-size-fits-all recipe. It's built with someone who already knows the domain sitting in the room. The modeling claim is the same as reweighting though. P of y given x stays fixed. We're just helping the model see a wider P of x. The third tool in the covariance shift toolbox sits at a different level than reweighting and augmentation, and it's worth being honest about that upfront. Transfer learning. Transfer learning does not assume covariance shift specifically. Its modeling claim is broader. It's assuming a representation learned on one domain is going to be useful in another domain, even when the inputs look very different. So this is less a covariance shift specific fix and more of a representation reuse strategy that happens to help enormously under covariance shift, which is why we keep it in our toolbox. So the idea is the following. In a lot of applications, say computer vision, this is the standard practice. An engineering team, as a first step, would go download a pre-trained model. In CV, in computer vision, that model would be pre-trained on ImageNet. And ImageNet is this competition that was held back in 2012 to be precise. So back in 2012, ImageNet, that year's ImageNet competition, kicked off the first big wave of modern AI when convolutional neural networks blew all the other competitors out of water when everybody's competing on this image classification task. Soon afterwards, people realized something striking. Take a CNN pre-trained on ImageNet, if we freeze the first few layers and stack a small task-specific head on top of the pre-trained layers, and we would get pretty strong performance even though it's a completely different task. Even though the pre-trained model, the first few frozen layers, they never saw our specific labels. And the reason that this would work is not magic, it's the visual hierarchy. Early layers of a deep neural network learns low-level features, edges, brightness, textures. We already saw that in our MNIST example. Layer by layer, those would aggregate into more abstract, more complex structure. And those low-level building blocks are useful across almost any visual task, which is exactly why these skills or representations would transfer. And later layers can now have the freedom to be more task-specific. So those are the ones that we would adopt. And we keep parts of the network that learn something universal. We let the parts closest to the prediction adapt to the new world. Every time someone adapts a pre-trained vision encoder or a large language model to a niche domain, that is the transfer learning idea in action. And that closes the covariance shift toolbox. We talked about 3 tools: reweight, augment, and transfer. They have this one shared assumption that the rules survived and only the inputs moved. Now to the second pattern, label shift. A quick warm-up before the math. Suppose we want to predict what the student is doing at, say, 2 p.m. from features like their location. And the labels include studying, sleeping, exercising, or having fun. During the semester, the mix might be 40% studying, 30% sleeping, 15% exercising, and 15% having fun. Over the summer, 10% studying, 20% sleeping, 30% exercising, and 35% having the fun. And we realize if we're trying to predict the student's activity, we should also consider if it's in the summer or during the semester, just because the class mixture is different. So the same evidence could lead to different guesses. A student at home at 9 p.m. is more likely to be studying over the semester than over the summer. And that is the gist of label shift. The labels themselves do not change. Studying still looks like studying. Exercising will still be exercising, but the mix is completely different. Now we look at an example we'll carry through this section, a code detector trained at a children's hospital. Imagine the training environment. kids catch 6 to 8 colds a year. So in that hospital, colds are everywhere. And the model learned that accordingly. When the model sees a patient with a running nose and a cough, well, the model would decide this patient probably has cold, and it's usually right. Then we move the model across town to MGH, an adult general hospital where adults catch only 2 to 3 colds a year. We ask the diagnostic question, well, what stays the same and what moved across this deployment? Well, we realize that the symptoms stayed the same. A cold still looks like a running nose, a cough, sneezing, regardless of if the patient is 6 or 46. What did change, what did move, is the prevalence. P, the probability of Y equals cold, the probability of the label actually being cold, having cold. That probability just dropped from common to slightly more rare. So the model arrives to the general hospital while it still is calibrated for a world full of colds, and it starts over-predicting them in the adults population. So even though the symptom evidence is still meaningful, the model just no longer knows how common colds are in this new environment. And that mismatch alone is enough to make a clinically deployed model flag healthy adults at an alarming rate. And let's see the math behind this example using some contrived numbers. So this time, we decompose the joint distribution of P of xy to be a new product. This time, it's going to be P of x given y, the features given the label, multiplied with P of y, the label distribution. Notice that the choice of decomposition matters. In the last part, we conditioned on the feature on the input x because the inputs were what moved. This section we conditioned on y, the labels, because this time the labels are what moved. We pick the decomposition that isolated the piece that actually shifted, following our modeling discipline. And for the code example, we might have the probability of a running nose given that the patient has cold being, say, 80% in both the adults and children's environment. But the probability of actually having a cold, the probability of the label, having a cold is perhaps 40% at the children's hospital and only 10% at MGH, the adults hospital. So the joint P of running nose, comma, having cold would drop from 32% to 8%. It's yet again the same conditional, different prior leading to different joint distribution. And that is the label shift signature. The modeling claim is that P of x given y is reusable. Only the class prior moved. Meaning that what each class looks like did not change. The mixture of the classes we see did change. And we could read that of the code example straight through this decomposition. Label shift just means the conditional is the symptom profile, and the label distribution is the prior, is the disease prevalence. And this decomposition keeps paying off because once we know which conditional is stable, the fix is essentially forced. And before we touch the fix, let's see label shift on a familiar dataset. Say we train on biased MNIST dataset. Sometimes you would also hear people call these types of dataset class imbalanced. So in particular for this dataset, digits 3, 9, and 0, they each get 100 examples. The other 7 digits, each having 14 examples. So our training prior strongly favors those 3 classes, 3, 9, and 0. At deployment time, we evaluate on a balanced test dataset where all 10 digits are roughly equal in quantity. So here we show 3 charts. The chart on the left is the per class accuracy. During deployment time, we see that majority digits sit comfortably above 95%. Minority digits crash down to 40 or 50%. The gap is label shifting action, where the rules of recognition did not change, the per class appearance stays the same, but the class frequencies the model expected during training do not match what it sees at deployment. And notice here, the model itself is doing nothing wrong. It's faithfully reflecting the prior we baked in. So the fix is going to be at the level of the prior, of the label, not the model. And the fix has a formal name, prior correction, which is basically the Bayes rule in disguise. And mathematically, we could write down this P of y given x under target domain as proportional to P of y given x under the source domain multiplied by a ratio. This ratio given by P of y under the target domain over P of y under the source domain. In plain English, this means that take our trained model's prediction and multiply that by a correction factor, a correction ratio. And that correction factor is how common each class is in the target domain versus the source domain. If a class became more common, boost its prediction. If it became rarer at deployment time, just reduce the probability. We're not going to retrain the weights. We're recalibrating the output probabilities at deployment time. So the models believe about, well, what a code looks like is still reusable. We just adjust how often we expect to actually see a patient coming in with code. So back to our biased MNIST from this slide. After applying this prior correction, we see that the minority class jumps from 40 to 50% up to 60 to 80%. And this boost is thanks to this correction ratio. In particular, for example, for class 2, the digit number 2, what we did is, well, we take the model's predicted probability and multiplied that with a ratio that's greater than 1. And how did we know that the ratio is going to be greater than 1? Well, because we know P of y equals 2, the class number 2's probability under the target domain is going to be higher than under the source domain. So that ratio, that P of y under target versus P of y under source, is going to be evaluated to a greater than 1 digit. So effectively, the predicted probability for class digit number 2 is going to be higher thanks to this correction. And if this correction factor feels familiar, well, that's because it really is the same idea coming from the covariance shift discussion, where we introduced this reweighting or importance sampling fix. And back then, we reweighted or used a ratio of the target versus source for the inputs. And here, since we are changing the label distribution, now the ratio or the correction comes in through the distribution on the labels. So whereas previously we double count or triple count based on how likely a feature is going to appear after deployment, now we double count or triple count a class label depending on how more likely is going to appear under the deployment. This correction factor might also feel familiar because it also linked to this famous medical test paradox. And some of us might have seen this 3 Blue 1 Browns video on this topic. Awesome YouTube channel, by the way. So in the video, it goes like this. A test comes in. It has 90% sensitivity and 91% specificity. I always have trouble saying that word. And the 90% sensitivity means that when a patient comes by and that patient really has a disease, this medical test is going to predict positive 90% of the time. Whereas the 91% specificity means that if a patient comes by and the patient doesn't have the disease, then this test is going to return false or negative, no disease, 91% of the time. So at face value, this 90% and 91%, they sound very reasonable. But the way that we interpret the test also depends on the prevalence of the disease. If the disease has 1% prevalence, a positive test means only about a 9% chance of actually having the disease. Whereas if the disease has 10% prevalence, then the same positive testing result would imply a 50% of chance that that patient actually has the disease. So it's the same test, same sensitivity, same specificity. The label, the prevalence distribution moved, and the answer, the posterior, the interpretation moved along with it. And this paradox is label shift dressed up in clinical language, and prior correction is exactly the Bayes update that resolves it. So here, yet another trick, and this one is even cheaper than recalibrating output probabilities. We could just change or adjust the threshold. We can show this idea in the simple example, simple illustration. There are 3 panels here. Left panel, a training distribution at a children's hospital where there's 60% of probability for healthy patients, shown in blue, and 40% sick in red. The dashed black line is our decision threshold, and it works very well in there. The middle panel here is deployment at an adult hospital. Now, this population has 90% healthy, only 10% sick, and the red curve has shrunk dramatically. If we keep the old threshold, we capture a large number of false positives from the dominant blue curve. So by holding the threshold fixed, we end up flagging lots of healthy adults as sick just because, well, there are so many more healthy adults around. And in a hospital setting, that translates directly into wasted tests, anxious patients, and clinicians burning out, all from one stale number. And the right panel here shows the fix. Without touching the model's weights, we simply shift the decision threshold to the right. We become more conservative. And this effectively is the same Bayes' rule idea. When the prior moves, the same evidence should lead to a different posterior decision. It's a very lightweight intervention for what could otherwise be a very expensive retraining cycle. But, and here's a very big but, there's still this big pending question of how much of a shift should we apply to the boundary. And that is yet another modeling decision. And ideas like cross-validation on a slice of the target domain data can help there. Ideas like monitoring, which we're going to introduce next time, monitoring the system, could also help. So let us line up the label shift levers ranked by their cost. At inference time, 2 fixes that never really touch the weights. The cheaper one is threshold adjustment. If healthy patients are 90% of deployment instead of 60%, we just raise the bar of predicting sick. The fix is literally just one number. Slightly more expensive one is prior correction. We multiply the model's outputs by new versus old prior ratio. It includes a few lines of source code change. There could also be training time adjustments, and that follows the same idea of the ratio adjustments. We could reshape the per class contribution. We could scale each class's loss by its target frequency, or we could literally just resample. We oversample rare classes and undersample common classes. In expectation, these 2 ideas are the same fix. One scales the loss, the other scales the data, and both would just encode the same modeling claim. So the principle here is to match the intervention to the smallest piece of the system that actually moved. And this principle is going to show up in every ML deployment we touch. Now let's put both patterns side by side. On the left, covariance shift, or mathematically it means P of X, P of features, P of inputs. That P changes, whereas P of Y given X stays the same. The world looks different, but it works the same way. Hopefully now this abstract description makes sense. And we could fix covariance shift by reweighting or augmentation plus transfer learning when representations carry over. On the right here, we have label shift, which means, well, P of Y, P of the label changes, and P of X given Y stays the same. So the world works the same way, but the mixture is different. And we could fix label shift by prior correction, threshold adjustment, or a class-weighted retraining. Identifying which pattern we face determines which fix to apply, because using the wrong fix for the wrong type of shift will not only not help, probably it would make things worse. That's why we keep saying that diagnosis before treatment. And here's a practical recipe for the diagnosis step. If we suspect input shift, we could train a so-called domain classifier. That's a separate model, tries to tell training inputs from deployment inputs. If the domain classifier succeeds easily, that is evidence of covariance shift. If it cannot tell the training inputs apart from the deployment inputs, there's no detectable input shift. And concretely, This idea just means we train a separate model on, say, daytime deer photos versus infrared deer photos. And if that separate classifier can separate these two, which naturally we should expect it be able to, then that's strong evidence of input shift. And if there's no such evidence, we should probably look at label prior. And for suspected label shift, the diagnosis recipe is even cheaper. We could just go and collect some target domain data. We can count how often each class show up and compare that to training time frequencies. So with the recipe in hand, let's test our understanding. Here we show a few fresh examples, and for each one, we ask what stays the same and what moved. Example number 1, spam filter. The spam filter is trained on Gmail and deployed on corporate email. If we think about it, well, what makes a spam email spam, that probably remains the same. But the type of words that you would see on a Gmail account is probably going to be more diverse than the corporate email, which tends to be more of a professional writing style. So the inputs, the text that you're going to see, probably are going to change. But the concept, the rule, what makes a word indicative of spam, that rule did not change. So this one here is quintessential covariance shift. Second example, sentiment analysis. An analysis algorithm that's trained on restaurant reviews and deployed on reviews written for an electronics store. A 5-star review on a restaurant probably contains words like delicious, whereas a 5-star review on an electronics store probably would talk about cool or latest technology. So the vocabulary used in these reviews, they're going to be totally different, but the connotation of what makes some description or some adjectives positive, that will remain the same. So here, this one, also covariance shift. Third example, disease screening. This one is the most similar to the code example we saw in the label shift discussion. But this time, instead of deploying at a different location, we're going to train the model during flu season and deploy them in a different time period. We're going to deploy that in the summer. And hopefully, because of our discussion, it's obviously a label shift case where the symptoms of flu, that did not change, but there's going to be far fewer patients actually having the flu over the summer. So the prevalence of the disease, prevalence of the label Y equals sick, that dropped. And finally, this last one is going to be a tricky one. Crop classification from satellite imagery, meaning that we take some satellite image and try to analyze what's the crop being grown on that land. And work from Sherry Wen's group looks exactly at this problem. They studied a model trained on French and South Africa farmland, and that model is deployed in India, and they analyzed the performance. So in this setup, what stays the same and what's changed? Let's take a second on this. Here we see that while French fields are large and regular, Indian fields are tiny and irregular. Soil tones and imaging conditions also differ. So the inputs look completely different. This is quintessentially the characteristics of covariance shift. But, and here's a medium-sized but, there's more to the story. And this one is more nuanced. I, for example, didn't know about this. It turns out France grows mostly wheat, whereas India grows mostly rice. Meaning that the class frequencies, that moved too. This is label shift. And that changes how the predictions should be made because, well, if you see the same image in France versus in India, you should already, when all else is equal, boost the predicted probability on rice more because in India, it's just more likely that a field is growing the rice. So in this example, it's both shifts happening at once. And in practice, this kind of mixture is actually the common phenomenon, where real systems, real deployments typically would have this tangled combination. Whereas in today's lecture, we have this clean separation of covariance shift versus label shift. That's more of a pedagogical convenience. And the stakes of these shifts, they are not academic either. Food security, supply chains, and policy decisions, they all ride on classifiers that have to keep working across these continents. So the implications are pretty profound. Let's wrap up with 5 takeaways. First, domain shift is not overfitting. The world changed, not our model's complexity or capability. Second, covariance shift means inputs move, the rules hold still, and we could fix it with reweighting or augmentation or representation transfer. Label shift means the class mix moves where each class looks like that stays the same. We could fix label shift with prior correction, threshold adjustments, or class-weighted retraining. The fourth point would be diagnosis before treatment. It's very wise to identify what stays stable before we go out and pick the right fix. And finally, every tool today, they work because something stayed invariant. Every fix we introduced today relied on some piece of the joint distribution surviving the shift. There's basically still a foothold we could stand on. And that sets up next time's harder question. What if the rules themselves move? And that is concept shift. It's where today's clean toolbox will stop working. And here's a quick MIT-flavored taste of it. 6-7, those 2 digits. In the MIT context, that used to mean the ECS and biology blended major. And if we trained a language model on old MIT forums or mailing list, that model would have learned that pattern, that mapping. But these days, 6-7 mostly shows up as a meme, so even though it's the same string, it carries completely different meaning now. And that is concept shift. Basically the rule of what makes meaning coming out of some inputs completely changes under us. And no amount of input reweighting is going to fix that. So when the relationship between input and labels change, there's no clean decision rule invariant left to lean on. Representations may still transfer, but the rule itself has to be relearned. So stepping back, machine learning is a technical tool for an ever-changing world. Our models are snapshots of one distribution, and the world just keeps on moving. So hopefully by today's discussion, every time we look at a trained model, we would be asking, well, where exactly is this model going to live? And what would be changing during that deployment? Because we would have to keep anticipating and keep adapting. Thank you, and I hope to see you next time.